Right. So before we really talk about what we're doing with these partial derivatives, we want to be able to solve a system of equations, and we'll see why that's the case, but we want to recall our abilities to solve systems of equations. So a system of equation is a set of two equations that we can solve together. Something like f of x, y, and g of x, y. Such that there's a point, we'll call it x naught, y naught, that solves both of these. If we plug these into here, we get the same thing as if we plug it into here. So we'll set those equal to each other. Cool. More specifically, a lot of the times we'll see that the function is equal to 0, and the other function is equal to 0. So we have two functions set equal to 0 that we want to solve. Cool. So we'll just look at some examples. Say I have 5x plus 3y equals 0, and 2x minus 3y equals 0. How do I solve these? Well, one thing I notice is that I add these together, I get rid of y. If I add these together, I get 7x, 3y plus negative 3y is 0, and that's just equal to 0. I can solve for x very simply now. I just divide by 7, and I get x equals 0. But what about y? If I plug this x equals 0 into either one of these equations, I'll get a value of y. If I plug it in here, I get 5 times 0 plus 3y equals 0. So I'll do that here. 5 times 0 plus 3y equals 0. This goes to 0, so I can just say that 3y equals 0. Or dividing by 3 shows me that y equals 0. So I get the solution pair of 0, 0. If you notice and take the time to do it, you can see that you also get 0 if you plug it in here. 0 minus 3y equals 0, minus 3y equals 0, divided by minus 3y, and you get that y equals 0. So it's very nifty, very cool. So you get a solution pair here. Do a little more complicated of an example, though, where we don't necessarily have the ability to just add them together. If I took the same system, but instead of plus 3y, I had plus 4y. I still want to be able to use the technique of adding them together and canceling out one of the variables. So what am I going to do? Well, I can multiply this top equation by 4 and multiply this bottom equation by 3. And what does that give me? Well, if I multiply this one by 4, I get 20x plus 12y equals 0. If I multiply this one by 3, I get 6x minus 12y equals 0. And what do you know? If I add these together, I cancel out my 12s. I get 26x equals 0, so x equals 0. And then plugging that into either one of the equations, I still get that y equals 0. So I get 0, 0 as my solution again. This is purely coincidental. We could have done something else to where this isn't the case. What if we make the situation a little more complicated, though? What if instead of just 5x plus 3y, I did 5x squared plus 3y? Instead of 2x minus 4y, what if I did minus 4y squared here? I can't just add these together. If I multiplied this by x and then tried to add them, I'd have this weird xy term. So instead what I can do is I can solve one of these equations for one of the variables in terms of the other. For example, this one, my 5x squared plus 3y equals 0, I can solve this for y in terms of x. So I get 3y equals minus 5x squared, or y equals minus 5x squared over 3. What do I do with this, though? Well, I can plug it into the other equation, and it'll pop out an answer for x. So let me do that. Over here, I have this 2x minus 4y squared. I can plug this value of y in here, so I get 2x minus 4 times this value of y, which is negative 5x squared over 3 squared equals 0. Cool. So all I've done is I've taken this value of y, I've plugged it into the other equation. Cool. Well, what does that tell me? Well, let me factor this or simplify it. That's 2x minus 4 times 25x to the 4th over 9 equals 0. Cool. Or, simplifying this some more, 2x minus 100x to the 4th over 9 equals 0. This looks like something that I can just factor, right? If I factor out an x, I get x times 2 minus 100 over 9x cubed equals 0. I didn't necessarily make the prettiest of examples, but I can solve this, and I get that, what do I get? 100 over 9. Actually, let me do this over on the clear side of the board. First off, I get x equals 0. X times something equals 0. X equals 0 is a solution. And then 2 minus 100 over 9x cubed equals 0. So 100 over 9x cubed equals 2. Can multiply by 9 over 100. So I get x cubed equals 18 over 100. Or x equals the cube root of 18 over 100. This is a kind of gross answer, but I just made up the problem on the fly, so we can't really hope for much. Cool. So that tells me that x is equal to the cube root of 18 over 100, which is probably some decimal value I don't feel like calculating. Cool. Now that we have a value of x, we have y in terms of x, so we can plug in x and get y. It's going to be a really gross answer, I can tell you that already. Cool. So we said that y is equal to negative 5x squared over 3. This is going to be negative 5 over 3 times x, which is the cube root of 18 over 100. And we're going to square that. Cool. And try to simplify this out some. This is going to be negative 5 over 3 times 18 over 100 to the 2/3. And honestly, I'm just going to leave it like that. It's a kind of gross answer, but again, I made up this problem. So y equals negative 5/3 times 18 over 100 to the 2/3. This again is probably some other decimal point, but this gives us our pair that is the solution to this system. I could have made a much easier system, but it's not necessarily the numbers that count as the process. So again, going through the process, I solved this equation. What was it, this equation? I solved this top equation for y in terms of x. I plugged that in to my other equation to solve for x. So I did that right here. Cool. And then, did I do it correctly? Hopefully I did it correctly. And then, using that, solve for the value of x, and then plug that value of x into y in terms of x, and got a value of y. Cool. So that's a system of equations, and we will use this to be able to find the minimum or maximum of a multidimensional object.